Morning to all our viewers and sir or who will join with us for today our webinars. Once again, I welcome on behalf of Parul University. I am Hetal Prajapati, Head of Diploma Electrical Engineering, PIETDS, Parul University. Today, we have the expert or webinar on the topic of capacitor voltage transformer. To, for this webinar, we have invited Engineer Rajesh Desai. Let me introduce Sir. So, Sir has passed his Bachelor in Electrical Engineering from MS University in 1977. Sir has also done the diploma in German language. Sir has wide experience of industry. Sir has worked in ABB Limited for more than 32 years as EDM and design head in instrument transformer business area. He is represented as expert of ABB India in ABB Corporate Study Group, IT Co-Design Committee, Sweden. Sir has successfully product development projects handled in circuit breaker, instrument transformer, and transformer boosting business units, right from co-design to type testing at various national and international labs. For example, CSI Italy, CPRI Bhopal and Bangalore, ERDA Baroda and Savli, IIT Madras in accordance with latest edition of IEC standards. Sir is also the in charge of site investigation team comprised of engineers from design, commissioning, quality and manufacturing departments for failure analysis of CT, CVT, circuit breaker up to 765 kV systems. Sir has also the membership and representations to various external institutes for ABB during tenure in ABB as well as in personal capacity like first technical member at Bureau of India Standard BIS, involved in finalizing standards for instrument transformer. Second is technical member at IEEMA Instrument Transformer Committee. So has handled international seminar Tech IT in 2014 in capacity of technical chairman, including scrutiny of technical papers. So has participated in international seminar Tech IT in 2010 and 2018, including scrutiny of technical paper. Sir is also the member in IEEE Vadodara, so super superannuated from ABB in year 2012. Sir is also the member of Society of Power Engineer. Sir has joined MS Luster Engineering Corporation, Navi Mumbai, uh, on 1st August 2012 till June 2015 and look after so many activities like as head design and development of high voltage instrument transformer and also in charge of manufacturing activity of instrument transformer till June 2015. Sir has developed so many following development carried out like designed, erected and commissioned 800 kV PD-free EHV lab in 2013, fifth in India, having zero ambient noise level. It is fifth lab of this kind in India. The lab got ISO 9001 in 2014 and NABL accreditations in year 2015 under guidance of SEP. So today we have very good amenity persons with us for next 1 hour. So I would like to request all our viewers and our students to join with us for next 1 hour. If any questions, any query, you can message me in my number. My number is 9662053087. Thank you. Sir, over to you.
Thank you, Hetal madam, for nice introduction. Am I audible?
Yes, sir.
Okay, fine. So now I would like to share my presentation on capacitor voltage transformer. Okay. My presentation is visible now.
Yes, sir.
Okay. So my introduction is already given. So that all know. Now today we will talk and we cover the following aspects. Capacitor voltage transfer, the basic principle of design, mixed dielectric, oil insulated transformer. Then IVT versus CVT. The IVT is an electromagnetic potential transformer and capacitor voltage transformer. So those both the difference we will understand. Basic construction features, functions, and selection of parameters of specification. And additionally, we will also talk about why CVT is preferable over IVT. So this is a general power system and substation view. After generation, the power is transmitted to over transmission line. There will be generator substation. It will go to another substation to down below, that is 245, 135. Then further down 72.36 kV. Then it will go to distribution network. And then the last, we will have a 450 volt three-phase system where we have our get all lights at our home. Now this is a schematic view of a substation where the you can see the first is a surge arrestor, then there is a bus post insulator, and the third is the CVT. This is how the CVT is located in the substation. Then after we have various substation components like isolator, circuit breaker, CT, etc. Now let us understand the basic difference between PT and power transfer, because power transfer you are normally know about this. What is it? Is a power transfer the power, that is V into Y, whereas potential transfer, which is CVT, is a part of PT. PT is a general name. That's why I put the potential transfer name. So CVT or PT, they transfer only voltage. They don't transfer any current. So the equation is Vp upon Vs is equal to Np upon, uh, sorry, here it is say Ns, holds good here. Ip upon Is is equal to Vs upon Vp does not hold here because Is is proportional to the instrument burden. We will study all this. What are the burdens which is connected to CVT? That is, we call it burden and not a load. Whereas that term is used for power transfer as a load, right? So here the equation is Ip upon Is is equal to Ns upon Np is equal to Vs upon Vp. And now the secondary voltage, in case of CVT, it is 110 or 110 by root 3 for all the voltage level, whether it is 800 kV, 400 kV, 220, 245 kV, or 145 kV. In case of power transformer, the secondary current can be any value as per the equation, as per the load which is connected to transformer. Uh, or this secondary output of the CVT 100 mA 3 get connected with the small current induced in the secondary winding. So it becomes 100 mA 3 into that current becomes a burden for the PT. This output is connected to meters and relays for measurement and protection purpose. We will further discuss on this function also. In a given switchyard, the location of meters and relays are in the control room, and the secondary voltage gets applied to the from PT output to the control room through cables. In CVT or PT, in the switchyard, the primary of PT is connected to bus, and PT measures the voltage and main bus and feeder. Whereas in power transformer, secondary current is proportional to the feeder's requirement. It is connected to bus through various load feeders, and it is power flows to at a various distance. Uh, in a switchyard, the primary of power transfer is connected to incoming line or bus from regulating bus voltage. As we have seen in the previous slide, the layout of the substation. Power transformer will feed the current to the feeder, and it is responsible to feed the current at all the feeders uh, as connected to it. Now, power system protection and written. Uh, Basically, the CVT, it measures regular voltage also, and then which one? Okay. Oh, oh. This is ah. So, uh, in all normal voltage as well as abnormal voltage is also monitored. So, what happens that during the short circuit, there will be a fault clearing by the circuit breaker. So, there will be a transient voltage coming to the system. Now, if it is out of the limiting value, then this voltage will be sensed by the CVT and it will be communicated to relay. And relay issues the trip command to breaker, and then circuit breaker trips and isolate the that particular over voltage feeder from the circuit. Now, this particular system is also analogical with a human body. Uh, our brain works like a relay, and all our sense organs like eyes, ears, nose, and skin, they are nothing but CVTs and VTs. And circuit breakers are our hands and legs. Suppose you see the fire in front of you, your eye will give command to brain that please run away, otherwise you will catch the fire. So what happens? Our mind will say, "Bhai, chalo yahan se hato." So you will run and go away. So this is how our human body works. So what I want to say that the instrument transformer, that is PT and CT and PT. Here we are going to talk about PT and CVT. So it is a very important component of the substation for normal monitoring of the voltage as well as protection. Now there are certain terms in a slide we will see. IVT. What is IVT? It is an inductive voltage transformer. We transfer primary voltage to the secondary voltage by electromagnetic phenomena, such that the secondary voltage is in phase with the primary voltage. Capacitor voltage transformer, same thing, voltage is transferred, but it is transferred through the capacitor divider, and it will has got a small electromagnetic unit, so designed and interconnected that the secondary voltage of the electromagnetic unit is substantially proportional to and in phase with the primary voltage. Applied to the divider. We will see the detailed slide, the concept of a capacitor voltage transformer. This is general view of the inductive electromagnetic transformer. It has got primary side coils, secondary side coils. In capacitor voltage transformer, you can see the two capacitors. In between two capacitors, there is a small intermediate PT is connected. This is inductive voltage transformer. Here, the core is same for all the windings. This is a view of already manufactured PT. You can see the on right side picture, a very big core is there, magnetic core. On that, all the windings, primary windings and secondary windings are also are wound on over there. And so, and the insulation is done for high voltage. So should I keep like this? Because I am using for the first time. Okay. This is the assembled units, IVT on the left side and right side CVT. You can see here this is a view of 132 kV. It looks same in the size approximately, but as you go higher and higher voltage, the IVT will become more bulky, whereas CVT will remain compact with the additional modular construction connected over it. If you see in the slide further. So this is a cross-sectional view, basically. The concept here is already discussed, mixed dielectric CVTs. Is the capacitor has got a dielectric which is of mixed dielectric nature. Uh, that is made of one polypropylene film plus one paper, then another third one is the another one polypropylene film. This particular polymer is a very fine dielectric, and that's why it is called a sandwich construction as well as it is called mixed dielectric. Now, coming to the detailed cross-sectional view, top side you can see the primary terminal. Then you have an insulator as an external insulation. Then this HF PLC device connection terminal. Now, this terminal is used for power line carrier communication purpose. And we have a terminal box where all the secondary output terminals are located. What you see inside is the intermediate PT. The detail of this I will show you through schematics. Then right side metal bellow which is provided for compensation because it is oil filled. So oil gets normally flows through this bellow and
Sir, network is poor, so sir will be joined very soon. Sorry for inconvenience.
As the certain number of layers are completed, it is taken out for the metal and it is packed up and then add it to the this thing. They are all connected in series. The big capacitors which get generated. This is the microfarad, and then when you connect it in series, it is a series connection. So it is 1 by C1 or 1 by C2, etc. So it converts into further lower capacitors that is coming in microfarad. Sorry, picofarad. Microfarad is 10 to 6, picofarad is 10 to minus. So just to start, how the concept has taken place some 50, 60 years before. You will have an idea that capacitor means everything is made of capacitor. So we try like this from two sides across the way to be but there's a got its own limitations because the current which is fed by it is very small and that is V to I is 0.20. This is very less. Our system requires for CBA 100. So I think that was so that we have to take this is to higher than the point. So here we one side we keep 100. The example is one, and two sides 20. So this what happens is capacitance of the to is to be inversely proportional, so it comes to around 20 yeah. So what did is connect 20 kV transformer. We call it bit. So primary side is secondary side is so it has got different uh, I mean different one, two, or three. That is so that is how the function of reactor, which is nothing but an inductive chalk. Uh, then, as I told you, the schematic cross-sectional view I have shown the lighting arrestor. So lighting arrestor is provided to particularly protect the PT, intermediate PT. In case of lighting, surge voltage and switching surge, in case of 400 kV, normally we have a very predominant lighting voltage and the switching surge. So this lighting resistor protects the PT primary side. Secondary side, we have a this 2 to 3 windings will be there, 10 volts, and then there is one FR circuit which is connected to damp out all the FR ferroresonance oscillations. We'll discuss in the last about what is ferroresonance. This is how the complete schematic view of the CVT seen over here. This is just again same thing. Now coming to the functions of the CVT. What for the CVT use? As we already discussed, it measures the voltage, transmission lines, and switchgear during normal and abnormal conditions. Uh, it also insulate the control circuit which is at a low voltage from the high voltage network. So this is an isolation through insulation, that is through capacitor banks, uh, and the output voltage we are seeing through the voltage transformer, 10 volts that we are seeing. It also used as a synchronizers between the two generating stations. Suppose we want to connect both the generating station through bus, then this PT can be used because you have to balance the voltage of bus 1, I mean generating station 1, and to that of the generating station 2. So this is used for that. The very important use of additional use is the power line carrier communication. We will see in the two next slides. So what you see is there is a substation A and substation B, and there is a transmission line already. The CVT C1 C2 part is used in that complete circuit. There is one wave trap which is nothing but an inductor. So it is working like a filter circuit. Here the voice signal is converted to high frequency signal in the bandwidth of 40 to 500 kilohertz, and then this signal is transmitted along the transmission line. It's like a telecommunication what we were having. So between two substations, any problem is there. Suppose even today, if mobile is not connectable or telephone lines are not there, then this particular communication is very important and it is useful for. So you can directly talk between the control room or both the substation, because we have various abnormality always happens. How much current is taken by the feeder, how much the power is available to feed in the next. So there are a lot of communication is always taking place between substation one and substation two. So this is a very useful this thing, particular device, which is now this communicating device that is known as power line PLC device, which is connected like this. It is connected to the, as I told you, there is a last point of the capacitor, that is C1 or C2, that is taken out on the over the tank, and to that, before it is connected over, this PLC device is connected to this. Now this PLC device is located in the substation itself. Wherever we have a CVT, which is under use of power line carrier communication, then this left side, that link is open, otherwise it is closed. That it has got a drain coil and spark diversion for protection of the where there is a high frequency signal is coming, then it should be actually yeah, this particular drain coil offers high impedance, and when there is a normal voltage, that is power frequency voltage, then it provides a low voltage. So that is how it works. And the spark gap is provided to protect all the voltage surges which is coming to this earth point. Now we are going toward the basic specifications. We have talked about the all applications. Now we have to see how we want to specify the CVT. Suppose somebody wants CVT, then what are their basic specifications? So those specifications are first one is PF rating, second is the ratio, third is the number of secondary windings, fourth is the rated burden on each secondary winding, class of accuracy, voltage factor, and finally the insulation level. PF rating, as I told you, being a capacitor is always specified the PF rating as by the customers. Normally 132 kV you can have right from 44 kV to 200 PF like this, and then 800 kV you can have at 2200 ratio. Normally, for example, primary side is 132 kV by root 3. Root 3 is coming because all these PTs they are connected from line to earth. So node root 3 always will come. Same way, secondary side 100 volt by root 3. So if you have two windings, then there will be such another winding will be there. And if it is three winding, then there will be three such voltage will be available for meters as well as relays. Uh, as we are talking about this number of secondary windings, mainly we have a two to three. One is first one is for metering purpose, other tools are for protection purpose. So normally this intermediate PT is provided with the three windings, right? Now rated burden. Normally rated burden, as we already discussed, it is output voltage into the current which is drawn by the relays or meters. So here let us assume that there will be this is what is you can see 30 VA is for metering burden and 170 VA for release burden. So total simultaneous burden becomes 200 VA, right? Because both the burdens are connected in parallel. So both will take the current separately depending on their VA requirement. That is the resistance impedance of the meters and relays. So here we have to see the voltage drop in the connecting wires because that will hamper the accuracy. So normally the voltage drop in the secondary circuit shall not be more than 0.1%. So you have to select the gauge wire of the cable connections of a particular size. It is shown over here that it should be minimum 6 mm square cable and it should be copper so that conductivity being very high, the drop will be very low. So it will provide the voltage drop. I mean the VA taken away by the cables is 0.2 V, 0.8 VA, and 0.2 VA is I mean the connections and of the relays and meters. This is very low because we have nowadays digital and numerical relays available. So total burden required is sufficient 30 VA. Now coming to the class of accuracy. Class of accuracy is very important for metering purpose because this voltage point is always connected to the energy meter. So correct output from the line voltage has to be there. So there is a point 1 class is there, point 2 class is also there, then there is a point 2s class, it is more accurate class. Then we have a commercial industry metering that is we can have a slightly low class that is class 1. Then you can have a this class 3 also for normal monitoring of the voltage. Uh, Now in total, I mean, as a summary of this, the three things we have to see. The CVT is, as you know, it is sensible to the frequency because the CVT is tuned with the 50 hertz in the laboratory because we have to compensate the capacity components and the with respect to inductive components so that phase angle always remains very near to zero. So, and also there is a voltage variation in the system. Here, the voltage variation system is from 80% to 120%. Frequency is plus minus 1% for metering and plus minus 3% for protection. And again, the burdens also vary. Suppose you are 30 VA, but it may happen that in some location the VA burden is just 35%. That is 7.5 VA. So the accuracy has to be at both the burden that is for 7.5 VA as well as 30 VA. So the bottom chart is given where with respect to particular frequency variation, how and voltage, applied voltage between 80% what will be the burden which you can connect so that you can have accuracy. So here you can see that uh, 300 VA at 49.5 to 50.5 hertz, whereas 0.2s class you can only connect 60 VA like that. Now, as the frequency variation increases, this connected burden has to be reduced. So you can see here when frequency goes to 48 hertz to 52 hertz, you can only connect at 30 base so that you can get the correct output of the voltage. So this is how you have to always see that the CVT is connected with the burden. Here, this is just a small view. It shows that you can see the bottom accuracy class is from 25 to 100%. It should depend the class. Now, as you know that 50 hertz, to get the 50 hertz is normally a problem. Our system has become so complex, so many generating power stations. If you see the network of India, it is equivalent to the whole Europe, right? Lot of this start our power supply from Kashmir to Kanyakumari by Power Grid Corporation of India. So there are a lot of disturbance may come, and that will always disturb the frequency. So CVT, that's how becomes very sensitive elements in the power system. But as per the rule of CA committee, the frequency has to be maintained by controlling the governor of the generator. So it is possible. But then when I was in ABB, I have checked that if you use the CVT instead of 50 hertz, if you tune it 49 hertz, which is normally prevailing in the system, then CVT can beat all the VM burdens as mentioned in the previous slide, and right from 48 to 50 hertz. So if this customer desires that yes, you can give our CVT with the tuning done at 49 hertz, if he is allowed, then we can do and we can give it. So it is about practicable solutions for the application of the CVT. This I have mentioned just for the information purpose. Now coming to the voltage factor. Voltage factor is actually what? A voltage factor is nothing but it is a operating flux density with which the particular PT is designed. So you normally this 1.5 voltage factor is there. 1.9 is also there. 1.9 when your or neutral is not earned properly, then the secondary side voltage is getting over voltage 1.9 times, right? And 1.5 times is always gets even though the neutral is earned. So you have to leave some space in the core design so that it does not get saturated, right? So this is how the voltage factor is specified for CVT, and so we have to actually test the CVT with this kind of voltage, 1.5 to 2.9 times. The duration is also limited here. Uh, 30-second duration you can allow when you have an automatic fault. I mean tripping by the automatic fault tripping the devices. If it is not there, uh, then you have to design the your CVT core, magnetic core, such that it can withstand for 8 hours. So it means that the 16,000 that is 1.6 Tesla is the operating flux density, but we cannot design with that. We have to reduce it to the half, and it will be zero point 0.8 Tesla as a working flux density, so that it can meet the voltage factor like 1.5 and 1.9. Now coming to the last basic rated insulation level. This level is applicable up to the altitude of 1,000 meter equal to 1,000 meter less than 1,000 height. For example, if we see 400 kV, you can have highest distance 420 kV. Power frequency withstand voltage is 630 kV. Lighting impulse is 1425 kV. That is always in peak. And switching impulse is 1050 kV. Now, as you go higher and higher altitude, like we go to the Bhutan side or Darjeeling side or Himachal Pradesh and all, where always the substations are located above 1,000 meter, right? So for that, what is required, because when you go higher and higher, the air density reduces, so the withstand capability in air, that is arcing, is I mean becomes more vulnerable. So what you have to provide, you have to increase the arcing distance. So you have to connect the that is insulator with a higher height, keeping the internal insulation as it is. The internal insulation is already with the oil inside and capacitor, so it doesn't get affected. Only external insulator is required to be updated to meet the higher altitudes. So there is one example has been calculated, and that is one example is there. 1.64 meter is there, and for that the altitude factor has been calculated, and for that purpose we have to test this insulator at 680 kV instead of 630 kV, and for lighting impulse 1539 kV peak in place of 1425 kV. Like that, switching impulse, which is to be tested at 1113 kV instead of 1050 kV. Now, we just show some slides how the capacitor moves the stack. As I already talked to you, that all the element coils are flat coils connected in series. So all microfarad comes to the picofarad value, right? So this is what you can see the EMU. Then you will have FR circuits consisting of resistor, capacitor, and FR choke. HV choke is there. That is nothing but a compensating reactor, and this is the bottom. How this capacitor coil is wound? It is wound on a very sophisticated machine like this. You can see the white are the rolls of polycarbonate film, and gray color rolls is nothing but a paper, tissue paper. Now you see this after the coils are taken out, they are made flatten like this, the second picture, and then it is stacked in the uh, together and measured for the required EM. This is the assembly after mounting the capacitor stack on the tank cover. Then the all the components are being assembled. Right? That's how the CVT is completed. Now coming to the last few slides, how the CVT is preferred over IVT. Now CVT, as I already told you, that CVT, so long as it gives very good accuracy ability, because it is possible, because the PP film and paper, they hardly get temperature rise. So there is no variation in the capacitance. That means the output voltage on the secondary side also remain constant. So that is one benefit we have got. Second is it is designed with a very low electrical stress, that is 20 volt per micrometer. That is nothing but 20 kV per mm. Acha. Then the third one is the CVT is a very uh, capable for to withstand the transient. Transient response is very good. And also there is a PLCC uh, application available with a wider bandwidth like 40 kilohertz to 500 kilohertz. So we just compare it, and we see how it is superior. First, CVT is a modular construction, easy to transport, easy to handle, and easy to erect. Whereas in IVT, it is a single and very bulky unit, as you go higher and higher voltage, you can see the it is being a single unit. The height of the top part is very huge. Second is CVT is cost-wise very economical. It is very low cost because there is hardly a iron core and copper inside the integrated transformer. Whereas in IVT, there is a lot of iron core and copper winding because the primary side is completely wound with the copper. Now the copper cost nowadays is 1,000 rupees per kg. Whereas here the coil, if you see the capacitor components, they are around 200 or 300 rupees per kg. Uh, the biggest advantage over here in CVT is that you have seen that all the capacitor coils are equally having equal capacitance and they are connected series. So whenever there is a transient voltage like switching surge and lightning impulse comes, this it offers it a very low impedance, being it is 1 upon the XC is equal to 1 upon 2 pi f c. So it offers very low impedance. So it happens that all this voltage is uniformly distributed across all the coils. And again, it gets equally distributed voltage point of view because all the coils are having equal voltage. So it will share the voltage. So whenever that means CVT is more capable and reliable product in case of high voltage surges. Reverse to this in IVT, it is being a inductive component. There is a big number of turns provided. So we'll have a unequal interturn and interlayer capacitance. So and also during a high frequency surge, uh, the being a inductive circuit, it offers a very high resistance. So it will establish a non-uniform electric field, and again because of the non-uniform capacitance, the first and the last turn of the PT will get higher voltages. So it may tend to fail. So manufacturer will provide higher insulation on the beginning and the last turns. Now when you provide a higher insulation, it actually interlayer capacitance reduces. Now, when capacitor reduces, it will have a more voltage. So there is no end to this. So there is to design to protect it from high surge is a very difficult case of IoT, and fine tuning is possible only up to the 125 because as you go higher and higher voltage, there will be higher and higher number of turns and higher number of the layers. So it becomes more vulnerable to fade at this. So this is how the CVT is more suitable product along with this application. So this is how I just complete my presentation. Thank you for listening.
Thank you so much, sir, for giving the valuable time to us to share the thoughts related to uh, CVT. Thank you so much, sir.
Thank you very much for organizing the webinar and giving me the opportunity to speak on the subject.
Thank you, sir. Have a great sir.